Welcome to the fourth lab of this course. We're going to observe the phenomenon on the RC circuit, especially the frequency response in the following experiments. It is recommended to understand what this frequency response stands to gain a fully understanding of the content of this lab. Experiment 1. We will measure the capacitance and equivalent series resistors by the RLC meter. Also record the measuring frequency. Because large capacitance is best measured in low frequency, therefore we could use the RLC meter shown in the figure to measure it. When we need to measure in high frequency, we will use newer model of RLC meter. In this figure, we've used 1 kHz to measure the 4.7 μF capacitor, with a result of 4.66 μF. This is an acceptable result. However, since we need to measure different capacitors, the 1 kHz may be considered too high. Therefore, we will use 100 Hz in this experiment. Experiment 2. We will implement a high-pass filter shown in this figure. Using its RC value to predict the frequency of the 3 dB point. Remember to include the computation in your report. In the first part of this experiment, measure the amplitude and phase of the output signal with different frequencies. Then sketch the frequency response in linear scale, dB scale, and also the phase. This will result in 3 different drawings. We require you to draw in the semi-log graph, which is shown here. Your drawings will resemble to this graph. You can see, since it is a high-pass filter, the signal will not degrade in high frequencies, but it degrades very fast in lower frequencies. Note that the figure shown here is drawn in dB scale. Now I'll talk about the details of the frequency axis. The scale of this axis is by applying the log function to the original value. We know that log 1 is 0. Log 10 is 1. Log 100 is 2. Therefore, you may observe that the value is 10 times more bigger than the previous value. The dotted line here represents 2 Hz, 3 Hz, 4 Hz, and so on. These lengths are also taken by applying the log function. Note that the dotted line here represents 20 Hz, 30 Hz, instead of 11 Hz and 12 Hz. For the second part of this experiment, use the frequency sweep function in the function generator. Set it to log scale. Starting frequency is 10 Hz. Ending frequency is 1 million Hz, with sweeping time 100 millisecond and with the marker option. Then connect the function generator to the circuit with the configuration written below. The result figure will be the amplitude frequency response. Compare it to the linear amplitude frequency response in the first part of this experiment. The concept behind the second part of the experiment is that we use the function generator to generate a signal which its frequency changes through time. Therefore, we could observe the changes on the oscilloscope, which records the amplitude of the signal through time. However, you cannot easily derive the frequency from the time observed. This is the reason behind the marker option of the function generator. The marker function will output another square signal through the sink that will change its value when the signal in the main has reached the desired frequency. For example, if we set the marker frequency to 240 kHz, then using the previous configuration, we could see the output result in the oscilloscope as this, which the yellow line here marks the location of 240 kHz. Now, the bonus lab. Using the oscilloscope, we could also observe the phase difference in the above configuration, using the Regal oscilloscope, giving you the following values. Note that in the Regal's oscilloscope, phase difference is always measured by signal 1 subtract the signal 2. Therefore, the correct configuration is to make signal 1 be our output signal and signal 2 be our input signal. Also connect the sync signal to the external trigger, with the trigger level set within the range of the sync signal. Also remember to use the average function to get better measurement results. On the Agilent oscilloscope, we could calculate the phase difference by both directions. Therefore, there is no need to change the original circuit configuration. Note that its precision is worse than Regal. Experiment 3. We will input a signal with noise to a low-pass filter. This signal can be generated using the function generator with the following settings. Then, design a RC filter that will keep the low-frequency signal and filter out the high-frequency signal. The criteria of keep and filter out is written here. The amplitude of the low frequency should be kept above 90% and the noise part should be kept below 10%. After succeeding, change your input to square and triangular wave with different frequencies into your filter. Compare and explain the cause of the output result. For the bonus lab, use the FFT function in the oscilloscope to see the difference between the noisy source signal and the filtered output signal. The FFT function will generate a figure that represents the strength of different frequencies in one signal. Take our generated noisy signal, for example. We could calculate from the AM modulation formula and see that we will get 3 different frequencies within the AM modulated signal. The first is the frequency of the carrier, then the modulation frequency minus the carrier frequency. Finally, the modulation frequency add the carrier frequency. You can see from the FFT result figure these frequencies respectively. Here is the result figure that you should expect. Before filtering, the source noise is large. After filter, the component of noise is decreased significantly on the FFT figure. That's all for this lab. The rest of the slides are supplements to the concept we just talked about. Good luck with your lab.